Alright, so today I want to tell you about the optimization of the performance of heavy web service that we are doing with one of our clients. I'm going to talk about the practices that we employ in order to make service more performant, better scalable, so that users of our web page won't have to wait too long for the requests. So the agenda of today's talk will be, first, when we should optimize. Then, how could we optimize queries in the database or API requests? And finally, we told a little about keeping things simple, because it helps us make things better, easier to read, but also perform better, as I'm going to show. First of all, let's talk about when we should optimize. Do not notice that in many cases, programmers attempt to optimize things too early. They just jump into conclusions that some macro optimization, some brilliant idea they have in their minds will make the service perform better, faster, and they become the heroes of the project. But in the end, when they do it, it barely helps. Sometimes it doesn't help at all. On the other hand, there are some crucial optimizations that can make project perform much better, several percent better. But first we have to spot those crucial bottlenecks in our code. So how could we tell which parts of our code are crucial and which are just something we have to write in order for our application to work the way we want it? Well, the answer to that question, how can we tell it, is measuring. In our project, we are using services because we are following the domain-driven design principles. So service is, well, something like that, simple object that takes a parameter of the request, return response as a future, because we want to do things asynchronously. We have some utility object, companion object that helps us create those services using functions that take requests and returns responses. And we also have the monitored utility function that wraps those services. It uses new Relic API in order to do some measurement on how we, using our services, how they perform. We're measuring how often they are called, how long they're executed, and how often they fail. With those data, we can determine that some of our functions are unreliable and we have to improve them. We can measure if some of our functions are too slow, and then when we spot which ones, we can look closer and look for all those bottlenecks that makes our clients unhappy with waiting for the responses. And we also can measure which of them are most often used and use those data to determine if our clients are using some services more often or less often.
So the microphone doesn't work.
Okay, sorry.
Could you speak a little bit louder? Yes, just a little.
Sure. All right, so basically we use those monitored services to measure the data we need, to measure how our services perform, which are the most useful, which are reliable, which are not. And with those data, we can determine which of them need to be optimized. So, well, we use it like that in our code. The get user billings is a service that takes user billing request object as a parameter object. It returns future of user's billing response, which contains the data we need. And the body of the service is created as we can see. The monitored service registers all of the data about our services under the name user services, get user billings, so that we know that all those informations we register is about this particular service. So once we learn that this particular service is underperforming, what can we do? First, we can look at the queries to the database it performs. So one of the most common problems in our project was N+1 query problem. And the other one was we're recalculating things all over again. Some services are heavy by design. We cannot do much about them, but we don't have to recalculate things time after time after time because nothing really changes about the data. It's only that we have one request after another for the very same situation. So we have to deal with stuff like that as well. So how we can deal with the former problem, the N+1 query? Well, N+1 query is often a consequence of using the active record pattern when we fetching some relationships where we're fetching the objects that our main object is related to. And then when we perform some queries on those fetched objects, we are often executing many small queries to the database. For instance, one query to fetch the collection, then we're iterating over the collection, and for each of those objects we are fetching the related objects. So instead of, for instance, 2 larger queries, we're performing a lot of smaller queries. Each of them has its own latency, slow down the processing, so we can do better. In smaller projects or prototypes or some crude applications when we don't have the need to perform those, hierarchical one object from the other, it's not much of an issue. So if you are doing some small log, some very simple crude application, you might not notice that this is a serious problem. But when our application grows bigger, when there are a lot of objects depending on each other, it slowly starts to kill the performance. We create a long chains of data fetched, we generate a lot of queries for even the simplest API requests, and we have to do something about it because the clients see that the service is slow. So let's look at our example. In our services, we are first going the user repository. We are fetching users as in the request. Then for each user, we try to fetch the contract he has. And for all his contracts, we try to fetch the billings. So, given the knowledge that the average user has 3 contacts and average contract has 2 billings, we can estimate that for each of those calls, we have 10 queries on the database on average, which is not really good when the user base will grow, those numbers will grow bigger as well, so it only gets slower and slower and slower. It will prevent our application from performing optimally, and our users would get annoyed pretty easily and pretty often. So in this particular case, how could we deal with it? Well, the simplest solution is if we aggregate our queries into something bigger. For instance, when we query user repository, we can get all the users. We can create a map from them. Then we can fetch the contract repository by the users. So in one query, we fetch all of the data we earlier were doing in several smaller queries. Similarly with billings. We also replace a lot of small queries with one bigger. So earlier we have 10 queries on average. Well, of course, the exact number depended on the specific case. Now we are guaranteed to have exactly 3 queries. We also use map to make it easier to retrieve the data from the collection, just like here. And in this way, we improved the performance of our application with a little because of the abstraction, because the former pattern is easier to read, but unfortunately it creates a big burden on the performance. It creates a big latency. This one performs much better, but the problem is that it's much more verbose. You have to type a lot of lines of code, so it's quite repetitive, boring, mind-numbing, but sometimes, unfortunately, is the only way to prevent all those small queries from occurring. What can we do when we want to cache the request? Because we know that we cannot do anything else when it comes to lowering the number of queries we are doing on the database. But still, there's a lot of them because we are using some API requests very often. For instance, when you are using some single-page website, when you are trying to update the data by querying the API in repetitive manner, for instance, once a minute or once every 50 seconds, when nothing changes, you'll get the same result each time. But still, our application would have to calculate all of this data again and again and again. And we could use that knowledge that those data change not very frequently to cache them, so that we would only query the cache storage and retrieve the data we already calculated in earlier requests. So this is our improved service, one when we already improved the performance by removing n+1 queries. But we still would like to improve it by putting the results into the cache. So how could we do it? We are going to use Redis. Redis acts like a key value storage. So basically, you have very limited abilities in how to use Redis on the API level. It's just a key value storage. You can only put the data under some key and retrieve data by some key. But one of the features of Redis is so-called hashes. It means that one of the keys is not storing longs, it's not storing strings, it's storing another associative array, so that we can use effectively 2 keys to store one value. And we can use that to our advantage with using some additional keys which store what is related to our results. For instance, let's say we have results of user billings for users 1 to 5, when we store the serialized value of our result. But we also store the results related to the user with ID 1, user with ID 2, and so on. And with those additional data, if we knew that, for instance, user 1 changed, we can retrieve all of those keys and invalidate all of those results. This way, in a very simple way, we use those limited API that Redis provides us to create some sort of tagging of the results. We can tag the results of our requests, tag our cache, and then invalidate of all the data we tag with, in this case with the type of the entity and the ID of the entity that was used to calculate the result. So when it comes to implementing it, we could do it, for instance, with some helper class. It will be used to tagging the results that we intend to cache. We also introduce some cache context. Redis needs to store the values in some way. The most universal way would be to store the data as strings or array of bytes. So in order to handle it, we would have to create serializer and deserializer for our data so that it could be transformed into something that could be stored into the Redis. And the other helper function is the function that could get the result and retrieve from it all of the entities and the type of and their IDs that are related to our results, so that we would know when to invalidate it. Then we can create some cache handler class that we can use to tag to the Redis using some higher abstraction. Here I put two most interesting functions. Getter path will use the value of the key of the request that we would like to use to name our result, the duration, because Redis invalidates data on its own after some time. We can tell it that it will be, I don't know, 10 minutes, 1 hour. It depends on the data we'd like to put there. Then we have to also put there the block which will calculate the value in case the cache is empty. And we also use the cache context, which will be used later on to serialize the data and deserialize data and check what entities affect the data, and as well as execution context, which we use to create some futures. And the other function is invalidate, which we use to simply drop all those cache values that are no longer actual. So how could we implement that? First, obtaining values from Redis would be pretty simple. We just ask Redis client for the value under some key, retrieve it. Redis client returns future option of byte array. We then map the future by obtaining the content. If there is anything inside, then we map it into the byte array. Then we put it into the deserializer and use those and obtain the data we put into the cache. So it's really simple. Just fetch the data from the Redis. Data are returned as future option, and after some mapping we get future option from the type T instead of future option of the array of bytes. How we can put the values into the data? That's a little bit more tricky. First we have to retrieve the tags, in this case the entities related to the value, entities used to generate the value. We generate the bytes from array of bytes from the object so that we can have the value that we want to store into the cache. And then we start the Redis transaction. First we include the actual value into the Redis. We perform it in here. Then for all of our keys, we'd like to create the hash that would create, the hash will be basically a part of cache request and empty array. We cannot just put empty objects there, so we have to put empty array to fill it with anything, fill it with something, just like we see here. So first we just create the cache for our value, and then we create the hash for all of the entities that were used to it, and put our value inside, so it could be used later on to when we want to invalidate the data. It's happening in those two lines. Here we inserting the actual request, and here we are tagging the entities with, well, we're putting the request under the entities that were used to create it. Then we can join those two functions together when we just simply first query the storage. If there is anything, then we just return value. And if the cache is empty, we calculate the value from the block that we pass into the function, and then we put it into the storage. Finally, we return the value, and then we can actually use it in our code. How we can invalidate? It's a little bit tricky. First, we have to retrieve. We're using here the entity keys. The entity keys that we wanted to invalidate. So we invalidate all the entity keys hashes, as well as all the cached results that were related to them. So first we are retrieving the entity keys from the Redis. It will be a map of values related to those keys. When we got all those keys, we can first delete the cache, but we also return those keys. Here we are basically retrieving all of those data. We are fetching the contents, so we know all the requests that needs to be invalidated, then we are dropping them, and the results from here are aggregated so that we can drop them all on this level.
Why are you using entity keys for invalidation, but simple strings for putting stuff into cache?
Sorry?
Why are you using entity keys for invalidation? Like, if
yes.
you go to previous slide, I guess.
Yes.
Yeah. So in the validate, you are
yes.
Use it as an argument, but in get or put, you're using value key, which is string. So
okay.
what's the difference?
Yes, sure. It's a good point. Okay, so it will be the easiest to explain with this slide. So basically, value key is this. Is the name of the key under which you store the results of your calculation. For instance, if you're calculating user billings for user 1 to 5, it will be here. The entity keys is this. We use it when you know that your user billings were generated using data from user with ID 1, 2, and 5. And for instance, you figured out that first user changed, so the data is no longer valid. What do you do then? You fetched this whole hash, then you get all of those key values from within. Those key values, you can just store a simple value with, telling that it's just there, so we're using its name and some empty value just to put it there. So we only want to retrieve the name. We're invalidating first user, so we're getting the content of this hash. Then we are getting only those names because it's the only thing interesting to us. Then we are dropping this hash, we are remembering this value, and when all of those entity keys are dropped, we are using those values because we save them for a later time to drop the actual values of the cache. It's maybe a little bit tricky because there's a lot of code and not too much place to put some comments. But basically, yes. Here you have the entity keys. It's putting. Here you are putting the value from the results. Here for each of you're creating or adding the values to the entity key storage hashes. So this part of code is kind of tagging your cache, and this part is actually setting the cache. And inside the invalidation, it's the other way around. First you would retrieve those hashes, then you are from all of those hashes you are retrieving the keys, you're dropping the hashes, you're dropping the keys. And this way you invalidated the cache by the tags that became no longer actual. And here's some example how we can use it in our code. We're creating implicit value of cache context for user billings. We're creating some function which will retrieve the entity keys, some serializer, deserializer. And in our code we simply use something like this. Cache handler getter put, we have to state the results type explicitly because it's partial application. So this type would not follow. Then you are putting the parameters, the key. See that the key is generated from the user ID, so that each time you change the parameters, it will land in another cache. But each time you use the same user IDs, well, I should sort them, but each time you use the same user IDs, you retrieve the same result from the cache store. And finally, we're just passing the future, which calculates the result in case the cache is empty, and the user billing context is passed implicitly. Okay, but what could we do when we are caching API requests? There's a small difference between simple database requests and API requests in that in API requests we sometimes use the data from the session, which user is logged in. Sometimes we use the data from the request, which parameters were passed, what was the format of the URL, and that also have to be incorporated into the knowledge about our cache. So we have to do some small modifications. This is our controller, some example which used user service we defined before. Here we simply are retrieving the contract and billing parts by current user and the user pass from the request to the service. Notice that there is some utility here which checks if user is authenticated, but it also exposes request object which has some data about the current request. What is the format URL, what user is currently logged in, and so on. And we will use those additional informations in our cache. So we're creating another get or put function. The only difference here is that we're using the data from the request. Here we want to use the information about the URL, the headers, for instance, the authentication headers, and the parameters passed into the request. With that, we generate some suffix and we append it to the key explicitly passed into the service. so that different values would generate different keys from the cache storage. With that, we don't have to modify the get or path function because simple change of any of those parameters will change the key of the hash and key of the cache, and so the values will no longer be the same. Usage is very similar to the previous one. The only thing we had to change was adding the requests that was passed into the action. Sometimes when we already dealt with the cache, when we already dealt with the N+1 queries, when we did all those more obvious optimizations, there's still not enough. Then we have to take a closer look at how we are using our API, how we are using our data, and then we might find sometimes very interesting things. One of my colleagues at some point have to struggle with the problem of a very complex API. Basically, the results returned by the API endpoint was very big JSON. It contained a lot of information. Here we use this service to generate JSON according to the whole format. So it contains all the links for all the entities here. It also contains embedded object, which contains all the objects related to the actual data. And this way we ended up with a huge JSON objects where, as we checked later on, almost none of those data were actually used on the front end. So we have a lot of data generated, a lot of requests, a lot of pressure on the database, and almost none of it was actually ever used. So then we started to identify what part of those data were actually used. And then we found out it was only a very small part of it all. In this case, it was just the contract and ID, just the billing and the ID of the user and ID of the contract. So with that knowledge in mind, we changed our service. We created additional method within billing repository so that it would return mapping from user ID to billings when we query it for billings by user IDs. Because each billing contains contract ID it's related to, we also didn't have to perform additional queries. So we replaced 3 queries by 1, and best of it all, result became much simpler, much easier to grasp, smaller. So front developers were also happier because they had less problem with knowing what they actually need. Those were the main optimization techniques our developer team were using when we tried to optimize the performance of our application. That weren't all the optimization problems, but the most common, the most annoying, and one that forced us to develop a lot of practices in order to get rid of them. So first one, so the summary that we can get from all of the experience is first that it's very useful to measure our services so we can figure out what needs to be optimized, what needs to be changed, what needs to be improved, because the guessing is futile. We should avoid N+1 queries, at least in bigger services, which are heavy on data, heavy on database. Every database query spared counts. Another things we learned was that caching queries and API requests when necessary helps. Of course, you have to use the data to identify which of the endpoints and which of the services needs to be optimized. You cannot just barely guess. And that keeping things simple and small is always useful because it not only improves the readability, it not only lessens the burden of the programmer, but sometimes it also optimizes the performance of our application. Okay, so now it's the questions time. Yes?
Tell me what kind of time profiler do you use, and is it a good idea to use the same time profilers as for the Java language? For example, I use JVisualVM, which is included in JVM, and I don't know, is it a possible idea to use the same tool in Scala, which is also...
Okay, so basically what we were using was New Relic. It's an internet service which exposes some libraries. You use those libraries in your code. It's targeting Java and also several other languages. With those services, they gather the data that, like the one I used before. Oh, here. New Relic increment counter, New Relic record response time, and in the case of error, New Relic notice error. Those are all services exposed by New Relic API. It's a commercial service. It gathers the data this way, and they perform some data mining on it so that you get already prepared results about how some of the parts of your code are performing, which you should better look on. It's basically a whole big service built around analyzing your data in order to tell you what you could improve, what goes wrong, which services are most often used, and which are the slowest, which are the fastest. Of course, you can replace those with, for instance, logging, and later on putting those into the R programming language or whatever tool you want to replace it. It's just an example. But New Relic proved to be quite successful in our project, so I use it in my presentation.
It's really a profiling tool because it does something, so you never know for sure if everything is working. It's more like a monitoring tool.
Yes, it's a monitoring tool, but it uses the data about.
Yes, and
it can be used.
A lot of nice bindings to Scala frameworks.
Yes, yes.
But there are some problems with it. For example, memory leaks. I don't know, have you ever noticed how much memory does New Relic actually consumes on your application side? Because sometimes it can be a lot, and sometimes it can be even more than you actually have. So you have to be very careful with New Relic.
Yes, in our code we use actually we're not using New Relic directly. We are hiding it behind the API, and then we can use different implementations depending on the situation. So sometimes it may be just null implementation when we know that some server is performed always well because it was proven and tested. In other services we might use New Relic, in some other we might use logging, and some other we might use combinations of them. I just used New Relic here because it was just simpler to show the API than introduce another layer of abstraction.
Have you evaluated DreamStat as an alternative for New Relic? Because it's a similar product, but it's cheaper, like a lot cheaper.
Personally, I have nothing to say about it. It's just because usually the managers and the architects that have the final word on which tool will be used. Very often those monitoring tools were decided by architects because they have some bigger picture. In our project we use, among others, New Relic, but perhaps they evaluated all the other tools as well. Some other questions? Don't be shy. Okay, so if there are no other questions, then thank you. I'm glad to have such a nice audience.